Well, first of all, thank you very much for this wonderful invitation from the University of Lund and the organizers of the Amazing Brain Symposium. It's a really great honor and a great pleasure in a moment in which higher education and science is under attack in so many places to be in a local community that has supported for 350 years a university. So it's a very unique moment, and I think you all should be very proud. I am very proud for you. And it's always good to know that I now know where, one of my heroes on TV shows come from. The Vikings I watch every weekend. So now I went to the museum and I was told that, my hero came from here. So this is wonderful. So I would like to give you an overview of the last 20 years of, what we have been doing very quickly to show why, for whatever purpose, that's what people sometimes ask me, why in heavens we decided 20 years ago to start linking brains to machines. A lot of people ask this question to me because they, in the beginning when we start doing this thing, the typical NIH reviewer would send us a letter saying, this is totally nonsense. Why are you going to do this? Well, in reality, when John Chapin and I decided to do this for the first time in the late 90s, we are just getting the technological ability to record in animals large numbers of single neurons simultaneously. We had worked for almost 10 years together to go from the typical one neuron that when I was a graduate student everybody was recording from to about 100 neurons in the mid-90s. So this is in fact the first time in my lab at Duke we recorded 100 cells from a rhesus monkey that was awake doing something. And when John and I look at this, at that time, hundreds of gigabytes that we were getting per day, we couldn't make sense of this. It was very complicated to analyze all this data. There are very few tools to look at these patterns of activity. And John and I were interested in studying how tactile information and movements are coded by multiple areas of the brain, as you saw in this beautiful talk we had before. So at that point, we decided that this could be a good analytical tool to start measuring in a quantitative way what can we extract in terms of coding information to generate movements from these samples of neurons that we're recording. By the way, I don't have time to show you, but we are recording now 2,000 neurons simultaneously. It took us about 20 years to move from 12 to 2,000, but now this is going to explode. This is going to go to hundreds of thousands of neurons in the next decade or so, I think. So this is what we did. We actually designed this apparatus. We named it a brain-machine interface, and the idea was to record electrical patterns, like you saw in the first slide, from multiple areas of a living brain performing a motor task, and ask very simple questions. What it takes from these populations of neurons to actually reproduce in a robotic device, let's say a robotic arm, the type of movements that these monkeys do normally when they're performing these motor tasks. What is the necessary requirements to get this brain to directly control this robotic device as if it were controlling the body of the monkey itself? Don't fight for a phone. It's very low behavior. Don't do that. Good. Keep it. So the idea then was this. Let's implant these brains with these fine electrodes that we use, that we developed together to record hundreds of cells. And in the 300 millisecond interval that it takes from a brainstorm to be generated in the motor cortex to generate a movement, in that interval, let's see if we can decode what is embedded in this storm in terms of motor commands, translate this to digital commands, and send it to a robot that can perform this task a little faster than the animal's own body would do when it is trying to move to get, let's say, a reward. And we close this loop, this brain-machine interface loop, by providing feedback from these devices, which, by the way, now we know, do not need to be a robotic device. They can be a piece of code. They can be a virtual body. They can be anything that you can control with brain activity. Moreover, this device doesn't need to be next to the animal. It can be in a different room, or it can be, as we have done in a few experiments, across the planet, in a different location across the planet, provided that you can close this loop in this 300 or 400 millisecond time interval, the interface is going to work. So the idea then was first tested in monkeys. Well, we did test in rats first, but people said the rats didn't count, so we had to do it in monkeys. And this is a rhesus monkey that was trained to use a joystick to basically move a cursor in a screen. So every time he was able to put this cursor inside of the target on the screen, he would get a drop of orange juice as a reward. While the monkey was learning to perform this task, and they love to do, as you're going to see in a moment, we are recording about 100 neurons from multiple cortical areas, and we are sending this to a wall of computers. We're running very simple multilinear regression mathematical models, trying to extract multiple kinematic parameters that could make a robotic arm that was located in a different room reproduce the kind of movements that the monkey needed to use to play the game. So it took about 2 weeks in the first experiment. So as this monkey was getting very proficient, close to 100% in terms of moving the cursor inside the target and getting the juice, our algorithms were learning to reproduce the movements very well in this robotic arm, so that we imagined that we could actually turn on this brain-machine interface and let the monkey perform the same task without actually having to engage the body, without having to move the body. Nobody believed that was possible, but because the number of neurons were absolutely tiny compared to the 100 million neurons that exist in the motor cortex of a monkey, we are only recording 100. But to the shock of everybody, including ourselves, this was what happened. This is our favorite monkey, Aurora, playing this game. You can see that she's very good with the joystick, and she's, as a good primate, is a good cheater too. Before the target appears, she's trying to reach the target, and she cannot do that because this target is going everywhere, 32 different locations on the screen, so she has to actually perform correct movements to reach the target. Well, she's, as you can see, is drinking a lot of orange juice here because she's getting every trial correct, about half a liter of orange juice for 1,200 trials a day, which is a lot for a monkey. But at this night, we realized that our algorithms have maximized its performance. And we decided to actually do what we have been planning for a couple years. We removed the joystick, we turned on the brain-machine interface, and we, waited to see what Aurora would do. And to our delight, Aurora just kept playing. But she kept playing without moving her arm. Everything that you see here, including the cheating in these trajectories, is derived from 100 neurons producing 3 vectors of velocity, Vx, y, and z. We've only seen 2 in this video, but we can do 3-dimension. And she's getting the reward, which is, for me, a Brazilian, is the proof that even in the United States, there is a free lunch if you use a brain-machine interface, right? So she was getting, after a week, the same percentage of correct trials that she was doing with her own arm. She was drinking the same amount of juice. But more interesting than that was the fact that since we were recording from multiple areas of the brain, about 120 neurons simultaneously at that time, we look to see the tuning properties, and I don't know what is happening here with my slide, but that's okay. The tuning properties of individual primary motor neurons in the primary motor cortex to the 2 different actuators that Aurora was using in this particular experiment, either her own arm or a robotic arm while she was immobile. Well, here you see this yellow diagonal. These are neurons, and this is directional tuning, and you see these lines for each neuron representing the breadth of the tuning curve of each of these neurons for direction. I have rank ordered them to create this diagonal just to show you that all directions in space are coded in a random sample of M1 neurons. This is what everybody knows. But this here was not supposed to have any yellow lines at all, because here the body is not moving. The animal is imagining these movements and getting a robotic arm that the animal is not even seen to move in a different room. This was supposed to be all blue, no firing in the motor cortex. But as you can see, the same neurons still have tuning curves. They're different than the original ones because they are now related to the robotic arm kinematics. Just by providing visual feedback from that robotic arm, in a matter of a few seconds, you can shift the tuning curves of these neurons, basically to make them become aligned with the kinematic properties of the artificial actuator that the brain-machine interface is controlling in real time. So that probably happens when we are learning to use tools. When we are learning to play the violin is being assimilated as an extension of the sense of self, each one of us, each one of the players. When we learn to bike, when we learn to play soccer, when we use any artificial device to perform a task, and we are getting feedback from this device, what this slide is showing to you, and it has been confirmed now by many other studies with all sorts of things, including avatar bodies and the rubber hand illusion, all sorts of things, is that our sense of self goes to the edge of the tools that we use to interact with the world. That was the first finding that was very interesting. But when John and I look at this very carefully, we realized that even though both of us were basic scientists, we still are, this had a very tremendous potential as an applied tool, not only to investigate how the brain operates, but perhaps, and this we publish, this image, believe it or not, now that there are 10,000 papers on brain-machine interface in the literature, I can barely joke about this because we tried to publish this image everywhere. Only Scientific American would publish in 2002 because people thought that this was completely nuts. That we could basically imagine that if you have a patient with a spinal cord injury, which makes the body below this level of the injury paralyzed, and the patient cannot feel anything below the level of the injury, what John and I suggested to restore mobility of these patients, why not using a brain-machine interface that would read in the motor cortex the voluntary motor intention of this patient to move, and then using a computational and mechanical bypass, get these signals and send to a new body, a robotic exoskeleton that this patient would wear so that he can imagine the walking commands, and this robot would be able to interpret them and actually make this guy walk again and receive feedback to actually incorporate the robotic arm, as you saw here, as part of the sense of self. Well, I'm not going to tell you 10 years of work to get to this point. I'm just going to show you the last experiment that we did to validate this claim that this could be possible in humans. This is now almost 10 years after the Aurora study that you saw. Now everything is done wirelessly. We are requiring, routinely several hundred neurons simultaneously from up to 12 cortical areas in these animals. And we can record in the basal ganglia too with deep electrodes. But what we did was to train these animals in the first task that involves monkeys using a self-driven car by a brain-machine interface. So we put these guys in electronic wheelchairs, and we made them learn to navigate in our lab to reach a pod where they can collect grapes. But to do that, we put them in random locations in a room. They have to imagine a trajectory. They have to imagine velocity vectors that will take them from the original position all the way to the pod to collect the grapes. And these are not limb movements. These are not moving the upper or lower limbs. These are motor tasks that no monkey has ever done. You don't see monkeys driving cars using a brain-machine interface in the streets of Lund, not even a bike. They don't bike either. So what we propose is that if you give a contingency to the brain, and the contingency involves getting reward, the brain is going to figure out what to do. And that's basically what happened. So you're going to see here, first from a camera on the ceiling, the monkey driving using a brain-machine interface with about 400 neurons, driving the wheelchair to the pod. And then you're going to see from the front, as the monkey is coming, and you're going to see a couple of things that are very peculiar about this driving. So the camera is on the ceiling of the lab. You see the monkey here driving. This is a helmet for protection, and this is all wireless recordings. So we are sending about 400 neuron streams to this processor here, and the monkeys figure out a trajectory to get there without moving the body, just moving the wheelchair. This is from the front. You see the monkey could care less about life. He just gets there, and when he gets close to the pod, he just collects the grapes and eats them. But he's controlling this two-dimensional driving completely by herself. So that gave us the assurance that our original idea in 2002 could work, that you could train a brain to control a device that is not at all like a body, like limbs, to basically move. But there's something else. Since we're basic scientists, we always keep looking at the brains of these guys. And I'm sure that this morning you heard about place cells in the hippocampus. This amazing discovery that was done by John O'Keefe and then by Dr. Moser's group of, having cells that respond to space in the hippocampus and grid cells in the entorhinal formation. Well, this is supposed to be because we have higher order processing in the hippocampus on top of the hierarchy of cortical structures. Well, let me introduce you to place cells in the primary motor cortex. Since we make these monkeys drive around the room, we could record these neurons at each location in space. And what we found is that a significant percentage of these neurons, 30 to 40% of these cells, actually have place fields. This is where the reward is. This is the zone where the monkey starts making movements to actually get the grapes. So you should have anticipatory motor activity around this location. But what we see here are different neurons have different spatial receptive fields. And the receptive field varies in relation to where the food is located, but not where the monkey is looking at. So if you make the monkey look to the pod or look away, the fields are consistent. This is primary motor cortex. We found that also in primary somatosensory cortex, in the very low levels of the hierarchy, suggesting that we have to rethink about the hierarchy. But let me go back to the application stuff. Once we did these experiments, there was a very good coincidence, particularly if you're Brazilian like me. Around 2009, we knew that Brazil was going to host the 2014 World Cup, Soccer World Cup. I don't know how big in Sweden it is. Looking for what I saw on TV the other day is big here too. But at that point, nobody knew what to do in the opening ceremony. And I had the nerve to suggest to the president of Brazil that we should have a scientific demo during the opening ceremony. Why in heavens have the dance, have the guys playing soccer? We are going to see 30 days of soccer anyway. Why not have a demo to show that people around the world can come and collaborate to get something concrete done in the spirit of this global enterprise that science is? And that's the reason we create this consortium, a non-profit consortium of scientists from 25 different countries that came together under the sponsorship of the government of Brazil to actually try to build the first brain-controlled exoskeleton that could restore mobility in severely paralyzed patients. And this is my acknowledgement already, before the end of the talk, because I start calling my friends, and I have a few. And 156 of them decided to join us. And what is beautiful about this, everybody opened up their patents, everybody opened up their intellectual property, nobody got paid, and we got it done in the spirit of this global collaboration that science is about. It has always been about, and I hope it will be for the time being. So, for that, we selected 8 Brazilian patients, young adults who had been paralyzed for anything between 3 to 14 years, complete clinical spinal cord injuries. These patients have shown no improvement. They are in the chronic phase where you don't expect anything to happen, but they could not move. They are all paralyzed, most of them from mid-chest down. They had no sensitivity below the body. And we decided to see whether we could use EEG, a non-invasive technique, to record brain waves and build an exoskeleton that could dialogue with this brain-machine interface that we developed. There are many steps in this training. We train these patients. We are still working with them now, 3 years after the World Cup. But the first 6 months were very intense because we had a date to deliver an experiment, which I don't think any scientist would like to do it. June 12, 3:30 on an open stadium surrounded by 75,000 people with 1.2 billion people watching. The night before, my mom invited me to go home to have dinner, beautiful Italian mom's dinner. And in the middle of the dinner, after 6 months of stress, my mom comes to me. She's a very famous Brazilian writer. And she tells me, you know, my son, if this doesn't work, not even mom can help you. That was the kind of support I got the night before. In any event, we built the exoskeleton. This is the first 12 degree of freedom electrical hydraulic machine that can be controlled by EEG or any brain signal. There are many modules that you can put it in there to get this controlled by anything. This is one of the patients being fitted to the cockpit. And one of the things that this is very special is because one of my friends, Gordon Schenk from the Technical University of Munich, developed what he called artificial skin sensors. These are very thin printed circuit boards that contain pressure, proximity, and temperature sensors, and you can basically Velcro this to the key locations of the exo, like the plantar surface of the feet, the knee, the hip. So we can generate tactile and proprioceptive feedback, because remember, these patients don't feel anything. So if you just put a guy in a robot and you ask him to control the robot just by thinking without feedback, he doesn't know what ground is. It's extremely scary. He is going to feel that he's floating on air. So Gordon instrumented the entire exo and created, together with Hannes Blur at the EPFL in Lausanne, a haptic display that allowed these patients to get the feedback coming from the sensors in the legs on the arms. And by manipulating the parameters of both frequency and the speed in which these signals are displayed in the arms, we discover a formula to generate a phenomenon that most of you have heard about called phantom limb sensation. We fooled the brain of all 8 patients, and all of them experienced this walking as if their legs were moving and their legs were touching the ground. So you see here a patient controlling an avatar of herself, walking on sand or grass or hot asphalt, and she's basically selecting with her search. We are using the brain as a computer here. She's selecting the best parameters in virtual space of the delivery of pressure in the arms that gives her the most vivid phantom limb sensation that she can experience. And each patient found the parameters that were best for them. So after this, I saw this scene many, many times, but there are 8 days during this process that were very unique, because these were the 8 first walking days of patients that have been paralyzed, some of them for 14 years. So this is one of them, a former swimmer who had a car accident, was run over by a car, was paralyzed from T6 down for about 6 years, and here's the first day that he actually walks. You see the lights here. These are the signals of the EEG actuator. He's imagining the walking. These signals are basically being transmitted to the central controller of the exo in the backpack, and now he's walking. And every time he touches the ground, he's actually experiencing the pressure of the ground on the surface of his arms. And he's telling us what he feels. There's a huge mirror in front of him so that he can associate the watching of his body upright again walking with the stimulation on the arms. And that reinforced the sensation that he's walking by himself. In fact, I don't have time, this is already published. We have psychophysical evidence that the exoskeleton was assimilated to this patient's sensory motor cortex as that robotic arm was to Aurora 19 years ago. So they basically felt that they were walking. And if you could hear in Portuguese when he finished, removing the curse word, you would hear, "I'm feeling that I'm walking again." That's exactly what we expected, that we dreamed 20 years ago. Well, I don't have time to show you the whole thing, and I cannot show you the actual kicking during the World Cup because the great organization called FIFA wanted to charge me 8,000 euros per second, to get this footage released, even though we did the whole thing. And since we didn't have the money, we couldn't have the original footage officially, and perhaps this is the reason half of them are arrested in New York right now. Maybe, I don't know. And every time we went to the field, imagine you're in Brazil, you're in a Brazilian stadium, there were these big Swiss bodyguards searching us for cameras, for cell phones, but they forgot one major detail. We're in Brazil. And there was a Brazilian neuroscientist in the group. And no Swiss will ever find a place that Brazilians can find to hide a cell phone going to a soccer stadium, ever. So we got some footage. Nobody knows how that happened, but it sometimes happens. So this is the moment before we went to the stadium. Juliano, 9 years paralyzed from T4 down, asked me, I need to do one more kick. I want to be sure that this thing is going to work because there are 70,000 people screaming out there. And we basically set him up. You're going to see what we prepared for the whole world to see with lights because we couldn't speak. We did, FIFA didn't allow us to actually talk during the ceremony. So what you're going to see is when Juliano puts the arms on the armrest, the exo starts blinking because it's connected. So he can start controlling it. When you see two flows of green and yellow, the brain is sending the commands to get this thing moving. So my student is going to place the ball, and he's going to deliver the kick. We were supposed to have originally 3 minutes to do this. 1 week before, they told us that we had 29 seconds. So we had to adapt in a hurry, but it happened. So Juliano turned on the exo. He's now making the decision. He gets his body right. He now sets the trigger, and he kicks the ball. And he didn't know, because this was a surprise, not in this moment, but in the field, we had one of Gordon's sensors right here. The moment he kicked the ball on the stadium, he actually felt the ball. And he started screaming to us when he celebrated, I felt the ball. Imagine what it is for a Brazilian guy who has been paralyzed for a decade to be in center stage of the opening ceremony on the soccer field in Brazil, paralyzed, and actually be in charge of the kickoff. That's what neuroscience can do, sometimes. But this was not the end of the story. We heard many beautiful presentations showing how the brain is plastic. And we didn't expect plasticity to play a major role in this particular thing because this was very intense 6 months of training in people that have been paralyzed for more than a decade. Well, a month after the World Cup, we brought Juliano and the other patients back to the lab to do our regular neurological examination, which was part of our RRB. But for the last decade or so, this neurological examination has been always the same. Nothing has changed. This is Juliano, sensitivity, dermatome mapping. He was a T4 when we started. On July 31st, he was a T11. He had gained 7 dermatomes of tactile sensitivity in 6 months of training. It was not perfect, was not fine tactile sensation, but he could now feel if you touch him, and he could tell which side of the body he was being touched with a needle or with a brush. So if you look at all the patients, as we start mapping this, overall, after 28 months, the average gain on dermatome sensitivity is 10 dermatomes. Juliano has regained 16. He now can feel the toes. If you touch his toes, he can actually tell you which toe you are touching, which foot you are touching. Well, in another life, when I went to medical school 30 years ago, before quitting completely medicine, people told me, if you see something on sensory, you should look at motor, because things usually go together. In the beginning, as I said, these guys were completely paralyzed. Their muscles were zilch, nothing. If you asked them to contract anything, nothing would happen. Well, 7 months later, look at this. In each patient, we start discovering that they were recovering voluntary motor control below the level of the spinal cord injury. What does that mean? You just need to look at what I like to call one of my patients, the ballerina. This woman was paralyzed for 14 years, complete clinical lesion, T11. After 1 year of training, we suspend her and ask her, try to do anything. And she did that. That's the reason I call her the ballerina. She's almost doing a plie. But in the beginning, is with the right leg. This is about 13 months of training, okay? This is a year later. We did the same test, but now we are recording EMGs all over her legs. And I asked her to do the same thing. I just said, do your plie. And she did this. First, she went there and moved the right leg as I expected her to do. Very beautiful. But then, she moved the left leg. We kept doing that for an hour. moving her back and asking her to walk in the air. And she was able to actually do that. And we were able to document this recovery of muscles all over the legs, all the way to the ankle. She's a T11 around here. So bottom line is, after several months, and all patients show some partial neurological recovery of this magnitude, to the point in which one of our patients is now walking without the exo, without any device, with the exception of a little bit of superficial electrical stimulation of the muscles using functional electrical stimulation in a non-invasive way, and a cart for balance. And this is what the guy is doing. He's now producing coordinated locomotor movements, voluntary movements. And since this video was recorded last November, he has crossed 4,000 steps in this system. So the recovery was not complete, but it was enough to allow the patients to actually regain some autonomous walking. In fact, when you look at the clinical classification, according to the American Spinal Cord Injury Classification, we started with 8 complete spinal cord injury patients. We now ended, one patient had to leave the protocol soon after the World Cup, but we end up now with 7 patients that improved, of which 5 of them are incomplete paraplegics now. Because not only they recover motor control below the level of the injury, but they now have tactile sensitivity below the injury. More than that, they have recovered visceral control, partial visceral control of the bladder, of the intestine, and partial recovery of sexual functions. In fact, one of the ladies in the group recovered so much visceral function that she decided to become pregnant again. And she fed the baby throughout the pregnancy and delivery of a healthy girl, not by a normal delivery. She had to do a C-section because osteoporosis of the hip was too high. Nonetheless, she felt the contractions. She felt the baby kicking, even though she was, again, a T11, So this is just to show you that plasticity is maybe much stronger than we think. In fact, we may have an anatomical explanation for what is happening. Sorry, I'm getting a little late, but this is part of the Brazilian DNA, sorry. When we did MRIs of the spinal cord of these patients, remember I keep telling you that they're clinically complete, meaning that they cannot move, that they have no sensitivity. Well, in fact, they are not anatomically complete in some cases. So a guy named Karkulas, way back in the 70s, have done autopsies in about 1,200 patients with spinal cord injury that were clinically complete. And he found that in 65% of these patients, between 2 to 20% of the white matter of the spinal cord may still be anatomically connected. That's exactly what we found. We found in half of our patients there was something still left of the spinal cord. And what I think is happening is that by triggering cortical plasticity with this training of the spinal cord injury, we basically make these patients allow their brains to reroute these motor signals to whatever is left in the spinal cord down to the periphery or up from the periphery to the body. And that was sufficient to basically get some partial neurological recovery, suggesting that brain-machine interfaces may not be good only for restoring mobility, but they may be enough through the process of plasticity to restore functions that have been lost. Since I'm not often here, I'm going to go 1 minute above, if you don't mind. Yes, I think people would appreciate. If they're Brazilians here, of course. And they are, because I met one on the square 2 days ago. So, I told you about a brain-machine interface that uses one brain. But who said it has to be one brain? Nobody. So a few years ago, we developed this, a shared brain-machine interface, in which 2 subjects collaborate mentally to achieve the same common goal, the same virtual movement of controlling the movements of a virtual arm. And we did that by mixing the brain activity that came from these 2 animals. So you can see them playing this. And what you see is that this monkey is controlling the x-axis of this virtual arm movement, and this guy is controlling the y-axis. And if you mix their brains, you actually can get the 2 to actually perform this test no matter where they are. They can be in different labs. They can be in different locations. In fact, if you put 3 monkeys together, what you see here is a dance of the 3 brains interacting. The objective is to get this ball inside of the circle. This is a 3D game, so this monkey is controlling X and Y, Y and Z, and X and Z. They have to mix their brains to get these things together. Well, when we did this game, what we noticed is that in seconds, without any instruction, and not even knowing that there are different monkeys in the room, the 3 brains synchronized. The 3 brains came together, and they became a brain, a super brain by itself, just with the reward and the visual feedback. So we decided to test this hypothesis because it became very interesting to us. So we put a guy driving a wheelchair, as you saw, and a guy observing the other guy driving the wheelchair with a vested interest. Because if this guy gets to the pod and collects the grapes, this guy gets juice. This is the observer, this is the passenger. Look what happens. The guy is driving with his brain. He takes a look at us, doesn't like what he sees. Takes a look at the monkey, doesn't like either. He goes to the pod, and he collects the grapes. When he collects the grapes, this guy collects the juice. That's the task. It's a social interaction task. Look what happened when we look at the 2 brains as the monkey drove through this room. They get synchronized, highly synchronized. This is 0.6 across brains. Just by participating in a social interaction, these 2 brains came together. This is primary motor cortex. This is not any association area in the parietal cortex, prefrontal cortex. This is not a hippocampus. This is primary somatosensory cortex. And to finish, just to say that when you look at this synchronous activity, what you see is you can reconstruct from both brains where the wheelchair is in space. You can actually tell from the passenger or the observer's brain where the wheelchair is in the room. You actually can tell the kinematics from both brains of the wheelchair, even though the guy is just sitting waiting to drink juice. More than that, you actually can tell what is the interpersonal distance between the 2 monkeys and what is the distance from each monkey to the pod, particularly the passenger, in primary motor cortex. So this is just to finish to tell you, yes, you can use brain-machine interfaces to study the brain. You can use them to recover functions. But more important than that, what this has shown to us is that even in lower cortical areas, we can see very complex computation going. And I suggest that this may be the basis of why we are so good social animals, because we established these synchronous brain nets, as I like to call it, and that's the reason we create these social bonds. There are many mechanisms, hormones, music, language, but that may explain why, a bunch of young guys in a trench in World War I, when they listen to the bungo of the English army, jump into no man's land to be killed, certainly 90% mortality, because that sound recruits circuits, synchronize them into a single entity, and they jump to certain death. Or, in another more better terms, when the Brazilian team really plays together in the right location and connects, when the chemistry of the team happens, I suggest is because the brains of the players synchronize and get the job done. Thank you very much.
Thank you very much, Dr. Nicolelis. I think we probably still have the cash box somewhere over here. Is that right? Oh, you're right. It's over here. You got it. And do you have a question too?
I actually do.
You do? Then go ahead and ask the question.
I was wondering if this kind of technology would work for, like, amputees, like prostheses.
Yeah, it has already been done.
Yeah, and in that case, would that be able to, like, compete with other technologically advanced prostheses?
You mean
like other kinds?
Other prosthetic devices,
yes.
You mean? Yeah, there are now prosthetic legs and arms.
Yeah,
they are in laboratory level at this point, but they not only allow movements coming from nerves or the brain to happen, but they have sensors to provide feedback.
Yeah, I know, but no, never mind.
Okay, pass the ball.
We have another question here. If you pass it over here.
Whoa.
Excuse me, can I please take a picture with you later?
Oh. Well,
Is that all right? Okay, thank you. Do we have any other questions before we wrap up?
there's someone there. Back
Someone in
there.
the back. Oh, in the very back.
Yeah, do
Okay.
a jump
Please
shot.
try not to kill anyone this time. Okay, thanks.
Wow.
That's
Whoa.
a good one. Yay, very nice.
has
Thank
talent.
So
Yes.
this technology is like obviously like allowing people to do things that they normally wouldn't be able to do. Other aspects of technology currently are taking away some of these tasks from people, like automated driving and other kind of automation. How do you think we navigate between these two?
Yeah, I think I got the gist of your question, yes. Believe it or not, I use technology a lot to do these experiments, but I'm very concerned about what immersion, our obsession of digital technology and our over-immersion in digital devices is doing to our brain. In fact, I have written a piece about that, suggesting that our brains are not digital devices, and they don't operate on digital logic or Boolean logic. But by the time we obsess on everything that we do, we measure our walking with now clocks, number of steps, we are on computers all the time, the brain is plastic. So if you give value, reward for you to behave like a digital system, your brain is going to start behaving like a digital system. And what I'm afraid is that through plasticity, that will shorten or curtail or minimize what is absolutely essential to be human, that is our more analog functions, like creativity, ingenuity, insight, all the things, intelligence, by the way, is human intelligence, because I don't believe in this artificial intelligence thing. I think it's a misnomer, it's misleading a lot of people actually right now. So there is a risk that if you are immersed on this type of logic, that you may affect the brain, how the brain operates. But what I'm talking about here, very focused, is how to use this to recover functions that have been lost. You see? But I agree with you that we need to think very carefully about what is the limit, how far we go in augmenting ourselves, because there is a limit that I believe if we cross, we may not be ourselves anymore. We may be something else. And I'm not prepared to cross the limit myself. Okay?
Thank you very much. A big hand to Dr. Miguel Nicolelis.
Thank you.